Hi there, I'm Jeremy Krug and this is my chemistry channel. In this video, we're looking at the states of matter and specifically how the states of matter can undergo changes and transition from one state to another. Now, if you haven't already subscribed to my channel, go ahead and hit that subscribe button and ring that bell so that you're notified of any future videos as I upload lots and lots of them all the time. Now, we're going to start with the three main states of matter. We'll start with solids. Now you're probably familiar with solids as having a fixed shape and a fixed volume. So if we want to think about that, you probably know how molecules are related to each other in a solid. If something has a fixed shape and a fixed volume, that means that the molecules are usually very, very close to each other, as you can see in this diagram here. So true solids are actually crystalline. And that's what something is if it's a true solid. So if you think of this ice crystal here, and this is a very beautiful electron microscope picture of snowflakes. We can see how the water, the ice crystals are crystalline there. They're forming these beautiful crystals, and some of these snowflakes are actually forming little tiny ice crystals on each other. So that's actually pretty neat. And that's what happens in a real solid. You actually have this very orderly pattern, this crystal lattice, as it's sometimes called, in a solid. And that's why we have these very nice and neat, orderly patterns in the atoms and the molecules here of a true crystalline solid. Now, how about a liquid? You know what a liquid is. It's the state of matter that has a fixed volume but no fixed shape. So for example, a solid is something like a crystal. We know it's not going to expand or grow very much on its own, and it doesn't flow, but a liquid does flow, doesn't it? It has a fixed volume. If you take 1 liter of water and you pour it into another glass, it's still 1 liter, isn't it? It doesn't start growing on us, and it doesn't shrink very much, does it? So liquids have pretty much a fixed volume, but they do take the shape of their container. So how are molecules related to each other in a liquid? Well, if we think of a water, like a little water that's been spilled here on the table, well, we know that the water flows, and that happens because the molecules are usually a little bit less acquainted with each other. In most liquids, they're actually a little bit farther apart, even though water is technically not like that. But in most liquids, the atoms and molecules are a little bit farther apart. That way they can kind of slip and slide around one another, and that's why that's why liquids will flow. So liquids do have just enough space between the molecules so that material can flow freely. So imagine water that's spilled on the table, or milk that's been spilled on the table. We think of that as being a liquid. Now, you might be thinking that there are some things that aren't really quite liquids and aren't really quite solids, things that are kind of in the middle, like plastic or jello. And what are those? Well, those are called amorphous materials. And the word amorphous refers to these materials that aren't really solids, but they're not really liquids either. So I gave you a couple examples. Jello is a good example of that, as we can see here. Or plastic. Your skin is a good example of this. Imagine if your skin and your body were made of pure solid. You were crystalline. Well, you wouldn't be able to move, would you? Fortunately, our skin and our muscles are basically an amorphous material, so we can move and we can flex. Our skin is stretchy to some extent so that you can move easily. And here's one that you may not have realized. How about glass? So some people say glass is a liquid. Not really. It's not really a crystalline solid either. Glass is an amorphous material. So it's kind of a solid, but it's not a crystalline solid. It has a little bit of a give to it. It's not really crystalline. So it's actually more like jello, believe it or not, than that nice ice crystal that we saw in the last section. Now, how about gases? We've talked about solids and liquids and the things that are kind of in the middle. Well, gases have no fixed shape, and they don't have any fixed volume either. So of the three main states of matter, a gas is the one that can escape its container. and it can just fly out into the room and take the shape of the container or of the room that it's in. So when we think about how molecules are related to each other in a gas, well, think of how a gas behaves. This particular gas in this test tube is one that's called nitrogen dioxide. It has kind of an orangey brown color to it, which is unusual because most of the time we're not used to seeing gases that have a color. But in this test tube here, we can see that this gas actually has a color to it, and look at how it's actually escaping from that test tube. That's what gases do. They tend to escape pretty easily. So in a gas, the molecules are really far apart from each other. In fact, we can say that the molecules are moving independently of each other. And so, this molecule is doing this over here, this molecule is doing this over here, and as we learned in the last video, or in a previous video, I should say, sometimes they do bounce into each other and they keep going with these elastic collisions. Now, those are the three main states of matter. Those aren't the only ones. We can talk about plasmas. You may have heard of plasmas before. This is the state of matter that has a really high energy. Usually, we can say it has the highest energy. It's essentially an electrified gas where atoms have been stripped of their electrons. And so where could you find a plasma? Well, the stars, like our sun, is a good example of a plasma. Usually it's very, very hot in order to have one of those. There are other cases on Earth where you could have plasmas, like lightning. You've all seen lightning, and so you see how that's an electrified gas, basically. That expansion of the gas causes that thunder, doesn't it? Neon signs. The inside of these neon signs have a gas that's electrified, and it causes it to light up in a plasma. If you've seen the inside of fluorescent lights, those are electrified vapors as well. That's a plasma. Maybe you have a plasma TV, or you have seen or heard of a plasma TV. That's got a small amount of plasma in it. Now, maybe you've played with one of these things here, a plasma ball. Sometimes they sell these at novelty shops. And yes, this has a little bit of plasma in there. You put your hand on it and it looks like it's almost shocking you or something, but that's a plasma. And so we have that. Now, there's another state of matter that maybe you haven't heard of. It's a fifth state of matter. It's called Bose-Einstein Condensate. Now, what in the world is that? Well, this is a state of matter that was only discovered in the last century. So we're talking about in the last several years. About the year 1995 is when Bose-Einstein Condensate was first discovered. And it requires an extremely cold temperature for this to exist. When I say cold, I'm not talking about the inside of your freezer at home or the North Pole or something. I'm talking about a temperature that's within 1 degree of absolute zero. So you'd have to have some of the coldest temperatures in the universe in order to have a Bose-Einstein condensate. Now, some weird things start to happen when you get that close to absolute zero. We find that particles of matter tend to lose all electrical resistance at these very, very low temperatures. And also, some weird things happen to atoms. Atoms seem, as far as we can tell, they seem to stop behaving like atoms, and they actually start behaving like waves of light at these very, very low temperatures of a Bose-Einstein condensate. We don't know a whole lot about these condensates. This is something that a lot of research still needs to be done on, but it's nice to know that there is this other fifth state of matter. Now, when we talk about states of matter, usually we like to focus on solid, liquid, and gas. In a first-year chemistry course, you're probably not going to spend too much time learning about plasmas and Bose-Einstein condensates. It's nice to know that they exist, but we're going to focus on the main three, on those big three. We call those phases. And when one of those phases turns into another, that's called a phase change. So the remainder of this video is going to be about the phase changes. So let's take a look at those. Now, we'll have our three listed here. I have solid at the bottom and liquid in the middle and gas at the top, just because gas has the most energy, liquid usually has less, and solid normally has the least energy of the three phases. Well, if we go from a solid to a liquid, there's a name for that. It's called melting, and that's a word I know that you've all heard of before. So a solid, it's got this nice crystalline structure, and as you add heat or add energy to it, the molecules move faster and faster and faster, and eventually they're able to break free of each other, and they're able to start moving around. So that's what happens when something melts. Now, if you go on and keep heating it up, eventually those liquid molecules are going to have enough energy that they're actually able to move faster and faster, and they jump out of the liquid and they move into the gas phase, and that's called vaporization. And that might be a new word for you, because perhaps you've heard of other words for changing from a liquid to a gas other than vaporization. I know you've heard of the next two words. You've heard of boiling, haven't you? Now, boiling is a type of vaporization. It's when you have very rapid vaporization at the boiling point. So that would be something like this. You have some water on the stove, and you see it boiling. It's actually bubbling. It's churning. The vaporization is taking place throughout the volume of the liquid. That's boiling. Now, there's another type of vaporization that's a lot slower. This is called evaporation. And this is when you have vaporization that takes place below the boiling point. And notice that evaporation happens when you have high energy molecules at the surface of a liquid. So I'm going to highlight that, at the surface. Evaporation only takes place at the surface. So that explains why if you take a cup of water and leave it on a table overnight, it's not going to evaporate very much. But if you take that same cup of water and toss it out on the sidewalk outside, especially on a nice hot sunny day, you have a lot of surface now, so that same volume of water will evaporate very quickly. It only takes place at the surface. So here's an example of, looks like there's some evaporation taking place there, and maybe something else too. Now, do you know the difference between boiling and evaporation? I imagine you probably do. It's kind of intuitive in our language. If we have a cup of water and it spills on the floor and it's not there the next morning, do we say that that water boiled off of the floor? Well, hopefully not. That's not what happened. We say it evaporated off the floor, right? Because I think we know what that means. And likewise, if we have some water and we put it on the stove to make spaghetti or something, are we going to say, I'm going to evaporate some water? No, that would be ridiculous. We say we are boiling some water. So I think we kind of know the difference. But here are the main differences. I'll just put these up here. Notice the temperature. Boiling takes place at the boiling point. Every liquid has a boiling point. We'll talk more about what that means here in the next video. Evaporation takes place at temperatures below the boiling point. Boiling takes place throughout the liquid. That's why you see the liquid churning whenever it's boiling. Evaporation is only at the surface. Boiling is very rapid, it's very fast. Evaporation is very slow most of the time. In fact, it can be very slow. So back to our diagram here. It's possible for a solid to go directly to a gas without becoming a liquid first. That's a process called sublimation. Maybe you've seen this happen to dry ice, which is solid carbon dioxide. It looks like it's smoking. Well, that's because it's going directly from a solid to a gas. That's sublimation. That also happens sometimes if you take ice cubes in an ice cube tray and put it in your freezer and forget about those ice cubes for about a week or two. Open up the freezer, some of those ice cubes will have shrunk down. That's because the ice will undergo sublimation right inside your freezer. Now we can go in the other direction. A gas turns into a liquid. That's called condensation. So you've heard of that before. This sounds like the water cycle, doesn't it? And a liquid turns into a solid. That's called freezing. So once again, when these molecules in liquid, they slow down, they're unable to overcome the attractive forces between them, and they start sticking together. And they are actually stuck Well, that's what we call freezing, and things are actually frozen that way. And is it possible to go directly from a gas to a solid? Oh, yes, it is. This is a process called deposition. And it's not that uncommon, even though the word might be new to you. This is something that happens all the time. If you've ever seen the formation of frost on a car or on the roof of a house, that's deposition. What's happening is the water vapor in the air is directly forming ice crystals on the surface of that object, like the car windshield or something. That's deposition. It's not dew that forms on the windshield and then it freezes. That's not how it works. It's actually directly forming ice crystals from the water vapor. I hope you learned something in this video. If you did, please give me a thumbs up. If you like what you saw, subscribe to my channel. Like I said earlier, I'm Jeremy Krug. I've been teaching chemistry for over 20 years, and I hope to see you again on my channel where we can learn some more chemistry together.